Okay, hi guys. Tonight we're going to go over some things from problem set 10 and then some review from problem set 9 as well if we have time. So I got requests for problems, a lot of the same problems from a lot of you guys. You emailed in your responses. So I think it was, I need to start with, I think number 8 from problem set 10. Yeah, 8 and 9 got requested a lot. And then also the review questions were requested. So I'll start there with number 8. I actually didn't get enough time to review tonight before office hours, so I'm going to be going through this with you guys, but we should do okay, I think. So I will just open up to problem set 10, number 8. Yeah, it's the pick a strategic situation. Is that one of the review ones? Oh, maybe you're right. Oh, yeah. Was it you that requested the centipede game? Did you request the centipede game? No, someone else did. Okay. Did you understand that one, number 7 on problem set 10? Because I got a couple of requests for that one too. Okay, I'm actually going to start just with all the review questions for number 10 because I didn't realize that number 8 was a review question. So it looks like all those reviews were requested. So I'm starting with the centipede game, which I went over last time we had office hours, but maybe it'll help now that I have someone live with me in the room so they can kind of field questions and ask me questions about that one because it's kind of a hard one. So I will start there. I'm also turning the volume on my phone so you guys can text in questions if you have them, or not text in, email in questions if you have them to me, and I should be able to hear it go off. Okay, so we start with let's see here, an extended form game, extensive form. So I'm just going to draw that same tree that you guys have there. Okay, so your Amy goes first. I'm just going to put A for Amy instead of writing it out. So Amy goes, and she can either pass or she can keep. And anytime someone decides to keep, the game ends, and the payouts are just as they are listed there. So if Amy keeps in the first round and never gives Betty a chance and never passes it to Betty, then the game would end here, and Amy would get 2, a payout of 2, and Betty would get a payout of 0. So then Betty has the same option. She can either pass or keep. If she keeps, she gets, Amy gets 1, Betty gets 3, or she can pass back to Amy. If Amy keeps that time, she gets, what is it? She gets 4, and Betty gets 2. Or Amy can pass one more time to Betty, who then gets to decide ultimately how the game would end. If she keeps it, then Amy gets 3 and Betty gets 5. Or if she passes it, the game ends with both of them getting 4. So that's the extensive form game. I'm going to draw different shapes around. Actually, I'm going to make Amy in red so it can look at different players more easily. Okay, so Amy goes, she gets to decide whether to keep and end the game or pass to Betty, and then the game keeps going on until finally, if they all keep passing, it ends after a couple of turns, and both of them getting 4 each. Okay, so when we want to convert this game into normal form, that means we're going to make one of those charts that kind of shows all the different move options that could happen in the game. So I'm going to separate. We're going to have chart. And I am just drawing these in, but I guess we wouldn't really know until we thought about it how big the chart has to be. But since I've already done this problem, I know that it's going to be this big, so I'm just going to draw it that way. Okay, I'm going to put all of Betty's moves are going to be up here because she's one player along one side, and then Amy's moves are going to be over here on this side. Okay. I'm also going to do one more thing that will help us to I'm going to do one more thing over here to help us kind of think about how to make this chart, which is going to be really helpful. So I'm going to number the moves over here so that later on you'll see why I do that in a minute. But this is move 1, this is move 2, this is move 3. Move 2 and move 4 are Betty, and move 1 and 3 is Amy, right? Okay. Okay, so now what we want to do is put all the different combinations of moves that each of these players could do in this chart, okay? So, for example, Amy's going to get to move twice, right? And in each instance, she's going to have the option to keep. Or she might just keep in one of her options. Or she might pass in both options. Right? So this is to say that Amy has the choice for move 1. These are all move 1. This first letter okay, so this first letter here, all of these first letters, K, K, P, P, indicate what Amy is doing right here. Her first move, she either has the option to keep or to pass. So, and then in her next move, she also has the option to keep or to pass. So we might live in a world where Amy is planning on keeping in both of her turns, right? Which would be a keep, keep. Or she might be planning on keeping here. She might, pass there. And so these are all the different options that she could choose. So one thing that's interesting to note is that in reality, if she ever decided to keep for her first move, then nothing would ever happen to the third move, right? That would never end up existing because the game will just end right there. But we're still going to list it in the normal form of the game for the sub-game perfect Nash equilibrium. You have to have all the possible options listed. Okay, so Betty has all the same options. She can either keep and keep, she can keep pass, she can pass keep, or she can pass pass. The difference is, Betty is doing moves 2 and 4, in each of these cases. So now what we're going to do is just fill in each of the payouts for each of these options. So if the players choose these strategies, these are different strategies. If Amy chooses this strategy, then based on which of each of these strategies that Betty might have, because she can have any one of those 4 strategies, we'll put in the hypothetical payout. Okay. So if Amy keeps in this first move, well, we already know what the payout is then. It's just going to be 2-0. And it doesn't matter what kind of Betty we're dealing with because it never even gets to Betty, right? The same is true in this situation because in this move again, Amy chooses to keep in her first turn, which means the game ends and Betty never gets to make another decision. Then we also have, okay, so now this is going to be a little bit more interesting here. So now we have that Amy's going to pass on her first turn. On the second move, which is going to be Betty's move, so Amy passes. The second move is going to be Betty's move, and in this situation here, we see that Betty would be keeping. So Amy passes, Betty keeps. So we end up with a payout of 1-3. Again here, Amy passes and Betty keeps in her first move, so we get a payout of 1-3. Okay, if Amy passes, so, and then Betty passes, so we have Amy passes and then Betty passes. What's the third move? So Amy passes, this is move 1. Betty passes for move 2, and then Amy. So what would happen there? Yeah. So Amy passes, Betty passes, Amy keeps. You get 4-2 there. And the same will happen for this one here. Amy will pass, Betty will pass, and then. Okay, so now this last one, move 1, Amy passes. Let's move 2. Yeah. So Amy passes, Betty keeps, then we end up with 1-3. Same right here, Amy passes, Betty keeps, we get another 1-3. Then we get Amy passes, Betty passes, Amy passes, Betty keeps. So we're going to get Amy passes, Betty passes, Amy passes, Betty keeps. Yeah. And then the last one, yeah, if they all pass, then it's going to be 4-4. Pass, 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 pass all the way down. If any of you guys didn't get a chance to try this one on your own before now, just thinking about it in terms of if you get another one of these, like on a test or something, and they're kind of challenging, one thing I would just start out by, doing things like this, numbering the moves in order, having 2 sides with 2 different actors, right? We have both actors on each, they get their own side, and then list all the strategies that they can have.
I guess strategies are pretty, both sides, right?
Well, it depends. Well, if Betty had a third option here, it might be different. Yeah, and if that was the case, then Betty would just probably have an extra term up here somewhere. So, or she would have, say this was like another option, we'll call it, then Betty would have might have a strategy of EK and then KB. It would really increase the number of strategies there were. And there'd be and then have to do all the possible options. Yeah, so it would just extend this chart to be a lot bigger if there were other options. But you could add another option.
Yeah, so he hasn't done this thing in class.
I don't know.
I guess Thursday, so it's probably that.
Okay, so when we identify Nash equilibrium, we just want to find out where no one would want to move from based on what the other person is doing, right? So I'm going to do this by circling the numbers where the person doesn't want to move. And then when we have both, you guys do it this way in class, where like you put a dot or you circle one of them, and then if both end up with a dot, then it's a Nash equilibrium. Okay, so this could be helpful in determining what the Nash equilibrium is, especially in bigger things. So for Nash equilibrium, again, we're just going to find in each of these situations whether or not the person would do better by moving to another option. And so I'll just kind of show you. Okay, so in this situation, if we're living in a world where Amy is planning on keeping in her first move, she and Betty were living in a, so this is the option we're looking at right now. We're living in a world where Amy is planning on keeping in keeping, right? Would she have an incentive to change? Would Betty have an incentive to change strategies based on this move that Amy did? In this case, we'll look at all of her different payouts, right? If she's here, she has no incentive to move anywhere else because it's all the same. And the same is true of all of those. So whenever she has no incentive to move, that's like a Nash equilibrium point for her. But it's only a true Nash equilibrium if it's also true for Amy. Okay, so we'll just go through Amy's really quick. So if we're living in this world, does Betty have a reason to move at all? You know, because she has nothing changes no matter what she does. She has no incentive to move from any other. Okay, if we're living in this world where Amy passes, would Betty have an incentive to move from a keep strategy to another strategy? A positive incentive. She might get 3 here, right? Can she get more than 3 by doing any of these other strategies? This one is Amy. The first, so yeah, so payouts are listed like that. So are any of these other options bigger than this option? Yeah, so this is another place where she wouldn't have any, where Betty wouldn't have any. Can't say the same for these two, right? Because if Amy's going to play pass keep, and then Betty would have an incentive to choose a different strategy from here, right? She would have an incentive instead of getting this 2 to get that 3, so she would want to. Not that she can know this in advance what strategy her person is employing, but this. That's how you figure it out. Okay. If Amy is going to pass, does Betty have an incentive to move from this strategy? Where would she want to move to? Yeah. So yeah, she would have an incentive to move to either one of those, right? And so these two are not going to be the optimal choices for her in this case. And neither is that one, because this one is beaten out by the 5, right? 4 is beaten out by the 5. So okay, now we're going to find out. We're going to flip it around and look at one of Betty's strategies and see if Amy has an incentive to change. So if this is the Betty that we're playing, and Amy is here, does she have an incentive to move anywhere else? No. If she's here, does she have an incentive to move anywhere else? No, but down here she would. So those I'm not going to underline. If we're playing in this world, where Betty's going to keep pass, and Amy chooses this strategy, does she have an incentive to move? No, neither does she there. Okay, what about in this world? If we're playing keep, or if Betty's playing pass, keep, does Amy have an incentive to move from this strategy?
No.
You sure about that one?
But she,
Look at all of Amy's payouts in this column.
obviously, I don't know. Yeah. No, she owes a 4.
Yeah.
So,
So this would be the where she'd want to be in this case, right? Okay, and then this one's might touch you too, so watch out. Would she want to, if we're living in this world where Betty is going to pass, where would Amy have an incentive to be?
um,
Yeah, so she would want to be either there or there. If she found herself here, she would have an incentive to change her strategy. Okay, so now we found all the places where each of these people would have no incentive to move. Anywhere where the second number is underlined, so Betty would have no incentive to move. Anywhere where the first number is underlined, Amy would have no incentive. Anywhere where they're both underlined is a Nash equilibrium, because neither player has an incentive to move, right? I will say when you're doing this the way that we just did with, thinking of, I'll just erase this row and do it again real quick, just for B right there. Okay, so when we're looking at, let's see here. So if we're living in a world, again, I'm trying to figure out for B, if any of these are the best option. Wait, was that what I was? No, I was doing A. Okay, so if we live in a world where Betty is going to be a pass-pass strat, she's going to employ a strategy like that, then does Amy have an incentive to move from here or here? But you just have to make sure that you're asking yourself, you have to really make sure that you're thinking about which number you're looking at, whether it's the first or the second number. And you just kind of have to logically work through until you're comfortable with, okay, if Betty is for sure doing this, then what does Amy want to do? Or, and that would give us whether or not that's a one. You just have to make sure that you state it to yourself in the right way. And that would be the biggest. I think that might have been something that I missed on a test or something. That is just remembering, okay, when I'm looking at this column, I look at this number and all that stuff. But if you tell it to yourself kind of like a story, if Amy chooses this, what would Amy, or if Betty chooses this, what would Amy want? Okay, so the Nash equilibrium are anywhere where both of these are underlined, so these are all Nash equilibrium. Okay, so now we're going to try and figure out which one the subgame perfect is. So the subgame perfect Nash equilibrium is the strategy for each player. It includes both player strategies, for which, so it'll be in terms of 2 letters and then comma 2 more letters, because those are the strategies. Okay. So the subgame perfect Nash equilibrium is a little bit different than regular Nash equilibrium, right? It's when no matter which one of these are all happening at different moments, right? This is moment 1, moment 2, moment 3, moment 4. No matter which of those we're looking at, the subgame perfect Nash equilibria will always still be the correct strategy, the most logical strategy for that person to employ. So, and you find it by working your way backwards through the problem. So we're going to start with this fourth, the last minute of the last move of this game here. So if Betty is here, what is the logical move for her to make? Would she want to get this payout or that one? Yeah, so she would want to keep, right? So if we're looking at the strategy like this, then Betty's strategy would be to keep in the second instance, right? She would keep move 4. Player A could also figure out, she could do this working backwards thing, and if she did that, then she would know that if she passes, essentially she's going to end up with this payout, right? Yeah. So she knows that B is a logical person, and she knows what B's payouts are, and so, or Betty's payouts are, and so she knows that given the option between 4 and 5, Betty's going to choose 5, which means that Amy's going to be stuck with 3. So then Amy's option becomes, do I want to pass and end up with this, or do I want to keep and end up with this? So what is Amy going to do in that third instance? Yeah, so this would be move 3. Going back again to move 2. Betty knows that Amy is going to choose this because she knows that Amy's logical. Because I know Amy's going to choose 4 over the 3 that I would give her. So Betty's going to be choosing between this and this. Yeah. And so what is Betty going to choose? So keep 2 here. And then once again, to get back to the first move, Amy knows I'm either going to get 1 if I pass it, or 2 if I keep it. So she's going to keep it there too, right? So the subgame perfect Nash equilibrium is a strategy, and so this is the strategy. But I could also, because I know what the strategies are, I could also tell you what the payout would end up being. But when you're actually talking about the subgame perfect Nash equilibrium, you're talking about a certain strategy. So the subgame, you might be tempted to say the subgame perfect is 2-0, but that's the payout of the subgame perfect.
Change that.
No, it's always going to be one of the Nash equilibriums that you found. Or I think it would be. Maybe that's not true. But I don't know. It might add in another Nash equilibrium. I'm not sure about that one. I could take time and think about it, but I don't want to waste your guys' time right now. But yeah, so this subgame perfect Nash equilibrium is this strategy and that payout. So these are all the Nash equilibriums, but only one of them is the subgame perfect one, which tells you pretty much how the game is actually going to end. If the 2 people are like logical, which you assume that they are when you're playing games. Okay, so that's number 7. Do you have any other questions on it before I erase it? Does that all make sense? Do you guys have any questions on that one? Email them in real quick. Otherwise, I will go on to number 8, which I might have to look at the slides for. We'll see. No, they can watch it live. I wonder if it's just a. Maybe it is just a minute here, but it's not. Yeah.
So John just realized that there's a little bit of a delay on the YouTube, so we just took a minute to wait and see for sure if there are any questions. Give you guys a minute to catch up in the video. Okay, number 8. Did you take a stab at number 8 at all, John? Okay. It's just a creativity challenge, I think. Okay, so number 8 on problem set 10 says to pick a strategic situation between two actors, i.e. a game in an economic sense, from a movie that you've recently watched or a book or your own life, and model that game in a normal or extensive form and include payoffs that you can justify and find your Nash equilibrium. I don't know which examples you guys have used in class already. This one is probably good to come up with your own example, but I'll help you come up with one. So the one I always think of is the game of chicken that happens in Footloose. Have you seen that movie, John? Footloose? Kevin Bacon. So there's a game of chicken in that movie, and Kevin Bacon I think he's playing chicken with some other macho guy, and they're trying to show how manly they are. Well, they're driving tractors towards each other. And so, if neither of them turn, then they crash into each other and they die, presumably, or something. I don't know. They get really bad injuries. But if one of them turns, and especially if the other one doesn't turn, then they're embarrassed, and that's costly to them too. So it's kind of like a lose-lose situation, unless you're the one that doesn't swerve, and another person does. So I'm gonna erase this now since I haven't gotten any questions on it, and draw that one. Okay, have you used a game of chicken in class at all? No. Okay. This isn't actually relevant, but I want it to be a game of chicken with Kevin Bacon. Yeah. Okay. So I'm just gonna do normal form. So we have Kevin has his own options, and Macho Villain has his options. They only have 2 options, right? They can either go straight or turn. Well, that's true. You could say that they could go one way or the other. That makes it that'll make it more complicated, but maybe that's a good reason for us to do it that way. Yeah. So let's assume it's a normal game of chicken and they can only turn or crash. So Kevin Bacon has the option to let's see, T equals turn, D equals go straight. Actually, I'm going to have TR equals turn right, and TL equals turn left.
Okay, so Kevin Bacon can either turn right, or he can turn left, or he can go straight. Macho Villain can either turn right, or turn left, or go straight. Actually, you know what, John, I'm gonna
Just
only
do one
include the turn.
turn.
Yeah,
Yeah,
just
we can
one
do
way of
that.
turning, because otherwise you have to like introduce like probability and stuff. And I don't know.
Right.
Yeah, and if the other person, yeah, so it'll just be complicated, and we have things like probabilities because they have to be considering. There's a chance that this person will turn the same direction I turn, and we'll both die in the end anyways. So then that would like kind of be the absolute. So turn or go. So Kevin Bacon can either turn or he can go. Macho Villain can either turn or go. We know for sure that if they both go, Kevin Bacon goes and Macho Villain goes, they're both going to end up with negative infinity, right? They'll crash into each other in tractors and maybe be mortally wounded. But there's also a cost for embarrassment. So what do we want to, we can just justify this right now. What do you think the cost? Okay, so I'm going to say cost of injury or cost of death equals negative infinity. Cost of being, how about the, do you think that the, John, this is just going to be an opinion question. Do you think the cost of embarrassment is less if both of you guys turn than if you're the only one that turns? Yeah, less embarrassed because that guy still isn't tougher than you. Yeah. So let's see, the cost of being embarrassed alone. Is, I don't know, what should we say the cost of being embarrassed alone is? -10. Okay. So, and then the cost of being, oh, I guess I can just put, so what do you think the cost of both players being embarrassed are by turning? Yeah. What do you think the benefit of like proving that you were not scared and the other guy was the only guy? Okay. Benefit of winning. Yeah, so I think that we can justify this, right? We just kind of did. Definitely the cost of death is going to be greater than the cost of embarrassment, but also the cost of being embarrassed by yourself when the other guy was brave enough to continue and go straight, or dumb enough, or whatever you want to say, is more embarrassing than it would be if both people went. Okay, so right here we have both people turn. So what does that mean that our payout would be? Yeah. So they both they both have this payout, right? Both players are embarrassed together, both -5. If Kevin Bacon goes straight and the Macho Villain turns, what is Kevin Bacon going to get out of that situation? Yeah, he'll get a +10 because he won, and the villain will get -10 because he had to pay the cost of embarrassment by himself. And then here it's going to be the opposite, right? Kevin Bacon would get the embarrassment by himself, and Macho Villain, if he goes, gets +10. We could also justify this in different ways. We could also say that if both
player's turn, they both get 0 payout, nothing changes. But I think it should be embarrassed, so that's why we can say that they should be embarrassed playing chicken and then both something else. Anyways, that's just an example from a movie or real life or whatever. There are way better examples, but that's just the first one that comes to mind when I think about game theory. Oh yeah, I got to do the Nash equilibrium. That's right. Okay, so now we're going to find the Nash equilibrium or equilibria. So first, let's look at if we're playing in a world where macho villain is going to turn. Does Kevin Bacon have an incentive to move from this strategy? Yeah, so he'd rather be here given this macho guy. What about given this macho guy? What do you want to do? You want -10 over -10, right? What about, okay, so opposite. If Kevin Bacon, if macho villain knows that Kevin Bacon's going to do this, what would he want to do? Yeah, you want to go straight. And if we're living in, if he knows that Kevin Bacon is going to go straight, what would he want to do? So if he knows that we're living in this Kevin Bacon world. Oh, was I think I should have done this. Oh no, okay, yeah. So if we're living in this world where Kevin Bacon is going to be the kind of guy that goes straight, is macho villain going to want this or this strategy? Did we do something last time? I'm trying to think because I feel like the logical thing is going to go turn. Yeah, those are the Nash equilibria. I'm trying to think of what the subgame perfect Nash equilibrium would be. Yeah, you'd have to look at every decision in the decision node, but since they make their decisions at the same time, I'm not sure what it would be. But it doesn't ask us that anyways, but I'm just wondering what it would be. Okay, so if you have any questions on number 8, just send them in real quick. Okay, so I'll just move on to number 9. So lobbyists have contacted the state of Utah with a request that food truck vendor license fees be decreased to encourage more vendors to open in the area. As a policy analyst at the legislature, you've been asked to determine how this will affect demand for food truck vendor licenses. One policy proposal decreases license fees from $1.99 to $1.50, with the quantity demanded being increased from 90 to 145. So what's the price elasticity of demand for food truck vendor licenses? What is the change in revenue? And then secondly, what's the change in revenue to the state? Mhm. Yeah. Yeah, the elasticity formula. So let's write down what's P1 and P2. P1 was 199, right? P2 is 150. And quantity 1, what was the original quantity? 90. And the quantity later is 145. Okay. So you just want to make sure that you if you're going to keep the, you're going to do, later minus earlier price. You want to do later quantity minus earlier quantity. Sometimes it might be tempting to do 199 minus 150 and 145 minus 90, but then you're switching the order. Yeah. So let's do P2 minus P1 over P1. So P2 minus P1 over P1. And then that's going to be all over Q2 minus Q1. And then it just becomes a game of the division problem, right? 150 minus 199 is negative 489 over 199. And here we get 145 minus 90 is 50. Can do it on calculator. This is negative 462 over so that's the price elasticity. And then, yeah, and then you can round it to whatever. Least, okay, so then next it says what's the change in revenue. So what would we do to get the original revenue? Divide. So for revenue is just how much money you're taking in, right? And how much money you're taking in is going to be the number of things you sell minus times their price.
Yeah.
So it would be, the revenue in the first case would be 90 times 199, which would be 17,910 in revenue. And after the change would be 150 times 1. What was it? So change in revenue is just 21,750 minus 17. That one's pretty straightforward. Okay, that's all for the review problems on that one, which I think was the most requested. Let me see what the next most requested is real quick. And you can email in any questions that you have on any of those before we move on if you'd like. Yeah, so it looks like it's just review questions from problem set 9 now. Open up that is problem set. Which one, where does the review start? Oh, there it is. It's just one problem? Oh, no, it's 2 problems. Okay. I think we might have done this one before, but we could do it again because a lot of people requested. So problem set 9, review question number 1. George operates Mountain West Burrito on the south side of BYU. Assume that Mountain West Burrito is the only place anyone can get a burrito in Provo. Demand or the willingness to pay is shown in the table below, and suppose that it costs $4 to make a burrito. Okay, so I guess I should just first start by duplicating the table that he gives us. So we have customer, willingness to pay, and then we want to figure out total revenue and marginal revenue. So we have customers A through H. Okay, and then he also gives us their willingness to pay. So person A is willing to pay $21, person B okay. So this is what we have, and then we also know that the marginal cost of each burrito is $4. Each additional burrito costs $4 to make. Okay, so we're going to use this chart to calculate total revenue and marginal revenue for Mountain West Burritos. For part A. Okay, so Mountain West Burrito is a monopoly. In this case, they said that this is the only place where you can get a burrito. So if Mountain West Burrito wants to sell burritos to the highest price possible, they could sell it for $21 and they would only sell one burrito. So they would get how much revenue? Yeah, $21. If they drop their price to $18, how many burritos would they sell? Yeah, because they would sell to this person and this person would still think it's worth $18. So they get $36 total in revenue. I'm just going to put in parentheses here. If they drop their price to 15, they'd sell to all 3 of these people, right? And so they'd get $45. Here they get 48. Here they would get So those are the different amounts of revenue that they would get based on this as a price. So in this instance, that was the price, etc. So, I mean, just before we even move on, we can kind of look at this and see kind of what's going on.
we see that they make a lot of money on that first burrito, and then gradually it looks like they're making less until right here it starts going down. They start making less revenue because they've decreased their prices so much. They've gained customers, but they've decreased their revenue. So that's just kind of what we noticed looking at that. Part B says, suppose it costs $4 to make a burrito. What is the socially efficient number of burritos to sell? So we're talking about social efficiency. We're talking about how many people value the burrito at least the marginal cost. Oh, did it say do not? Oh, and per, oh, okay, yeah. Sorry, I thought it was going to be this part. Yeah, so sorry, before we move on to that, I'm just going to do the rest of part A, which I missed, which is the marginal revenue. So marginal revenue is how much additional money would Mountain West Burrito get if they did lower their price? And so how much money, additional money do they get by selling that one extra burrito each time? So by selling this first burrito, they get $21. That first burrito, they get a lot of extra money on. When they move from selling one burrito to two burritos, so if they go to this price point, their total revenue increases from 21 to 36. And so that's a marginal revenue of 15. So that next burrito, they made $15 on it, but it only costs $4 to make. That's a pretty good deal. Here it goes from 36 to 45 for total revenue. So the marginal revenue is what? Yeah. Here it's 3. Here it's -3. Here it's -9, -15, and -21, -13. So how much revenue they get from selling one additional burrito? That's what that one is figuring out. Okay, so now I'm going to go to part B, which says, suppose it costs $4 to make a burrito. What's the socially efficient number of burritos to sell? If this wasn't a monopoly, then the socially efficient number would be however many people value the burrito, their willingness to pay is at least as high as the marginal cost of making the burrito. Yeah. Oh, it'll go a little bit farther than B actually. There's a willingness to pay. Where is willingness to pay stop being above $4? Yeah. Yeah. So he would sell burritos A through F. And Mountain West Burrito would sell 6 burritos. Because here we see person F values the burrito at $6, which is more than the cost to make a burrito, right? Person G doesn't value it as much as it costs to make it. So socially, even when we're thinking about socially efficiency, like these people don't get. Okay. And in that case, how much do you think that the burrito would sell for? I'll give you a hint. There's multiple answers. For the socially efficient amount. Well, they couldn't sell it for over 6 because then person F wouldn't buy it anymore. So it would be between 4 and 6 actually. At least the cost, but not any more than what this person was going to pay. So if this was a socially efficient outcome, burritos can cost anywhere from $4 to $6. Part C says that George decides to sell the burritos for $6. So what's the surplus for Mountain West Burrito? And what's the surplus for customers? Yeah. So Mountain West Burrito decides to sell for, let's see. The price equals $6. We know that the cost to make them equals $4. And the number that they'll sell, the quantity is all of these burritos A through F. 1, 2, 3, 4, 5, 6. So Mountain West Burrito would get the revenue minus the cost for each burrito. That gives you the revenue per burrito, or the surplus per burrito, times the number of burritos. Yeah. So 6 minus 4 times 6 equals 12. Figuring out the consumer surplus is a little bit more involved for this part. Consumer surplus would be different for each person, right? Because so he's selling them for $6, and yeah, so the surplus would be the price that they're willing to pay minus the price that they did pay. So this guy's not getting any surplus. He's getting exactly what he's worth. This person is getting 3 in surplus. So, and this person is getting 6 in surplus. This person is getting 9. 9. The next person is getting 12. The next person is getting 15. So if we add all those up, then we get the total consumer surplus. So 3 plus, so 18 plus 12 is 30 plus 15 is 45. Is that what you said? 45. So that's the total consumer surplus if burritos are sold for $6. And this is the producer surplus. So we see that consumers are getting more surplus than the producer is. So for D, if George decides instead of selling for $6, so if instead of selling for $6, George decides to sell burritos for the profit maximizing amount for him, because he's a monopolist, so he could do that, where would he want to sell? So the rule for this is that you want to find the price for which marginal revenue is equal to marginal cost. And we might not find a place where they're exactly equal, but we definitely don't want to go below. We definitely don't want to sell when marginal cost is greater than marginal revenue. Yeah, so this is marginal cost, this said. So we want to sell up until, we want to sell up until the point when marginal revenue is no longer greater than marginal cost, which is, so he wouldn't sell this burrito. Yeah, so he'd only sell it to C, which means he'd be selling at what price? Yeah, he'd sell burritos for $15 a piece. He'll sell 3 burritos, $15 a piece, and then his profit will be his, how would you find profit? The cost. Yeah, right. So it would be marginal revenue All these marginal revenues minus the marginal cost.
And then we just add up all those values.
That was the subtraction.
Uh, yeah. Um, 3. 21 minus 4, 17 minus 15 minus 4, and 11 minus 4 is 5. So yeah, and 33, so that's per D. And another way that you could figure out the total profit would have been to multiply the find his revenue. So his total revenue would just be 15 times 3, 45 minus $4 per burrito. So it would have been 45 minus 12. But you could find it with the marginal revenue, or you could find it with the willingness to pay. Either one. Okay, so how much surplus was lost by setting the price at the monopolist profit maximizing price? So there are 3 people that, so we're, for the monopolist profit maximizing price, we're only selling to these people. But previously we were selling to all of these people. So whatever surplus everyone was getting down here before is no longer existing, right? So you could just subtract their surplus that they were receiving, which would be their margin, their willingness to pay minus 4 for each. And that would be, if you added all this up, that would be their lost surplus. So 8 plus 5 plus 2, so 15. Yeah. Okay, so if we want to know how much surplus is lost, we can look at how much. So before we just did the willingness to pay minus the cost of making the burrito, or minus the price that he was charging, right? Yeah, because before they were getting, oh, I think I wrote the wrong name. Before the price was $6 a piece, so you just subtracted 6 dollars. That's how much it cost to make the George originally in one of the problem parts of the problem said. Yeah. Yeah. So we lose all the surplus that these 3 people would have gotten at that $6 price. Yeah, $6 and $2. Although he was getting some surplus too there for each of those. You need to take into account. So this would be, I guess, only the consumer surplus that's lost. But you could also add an additional 2 for each of those.
the difference between that $6 price and $4 to figure out what he lost in the surplus. Yeah, I want to know what the total surplus loss is, so you can go back to actually subtracting the marginal cost. And you can get a 15 for the total cost for loss. Does that make sense? So when I did the -6, I was only looking at consumer surplus. But when you subtract 4, you're getting into surplus.
Yeah. Okay, so that's that problem. Do you guys want to email any questions that you have? Okay, so now we're going to graph that for problem number 2. Okay, so we're going to graph all that stuff on number 2 that it says to do. Right. Do this on the computer screen. Looks like it's really dark over there. I did turn it, it just hasn't caught up yet. But for some reason, it just looks really dark back there. Does it look okay? Like, I don't think I'm gonna see if I can just share my screen with you guys and explain it that way, because I've got the key. I'm gonna try using the key really quick and just sharing my screen with them so they can see it, because I'm just worried that they won't be able to read and see everything.